Welcome to bmac.math tutorial. Subscribe our channel and hit the bell icon for freshly uploaded contents. This is a question from NTA CSIR Net, Assam and Meghalaya examination. In this problem, we are given a system of nonlinear ordinary differential equation x prime t and is equal to x square plus y square minus 2x and y prime t is equal to 3x square minus x plus 3y, and it is given that 0 0, that is the origin, is a critical point for this system of nonlinear ordinary differential equation, and it is asked to find the nature of this critical point. So before going to solve this problem, let us recall the technique of linearization about a critical point. For this, let us consider a system of nonlinear ordinary differential equation given by x prime t is equal to f of xt yt and y prime t is equal to g of xt yt. Obviously, this system is a autonomous system, and a critical point, a point x star y star, is said to be a critical point if both the term f and g are vanishes at the critical point x star and y star. That is, f of x star y star is equal to 0 and g of x star y star is equal to 0. Now, in order to linearize the system, we consider the Jacobian matrix J evaluated at the critical point x star y star, which is equal to del f del x and del f del y, del g del x, del g del y, evaluated at the critical points, and then we will calculate its eigenvalues for, say, lambda 1 and lambda 2. Now, the nature of the critical point and its stability will depends on the nature of its eigenvalues. If the eigenvalues are real and of same sign, then the critical point will be a node, and the node will be a stable node. Sometimes it is also called a sink if both the eigenvalues are negative, and it will be an unstable node. Sometimes it is called a source point if both the eigenvalues lambda 1 and lambda 2 are positive. Now, in case 2, if lambda 1 and lambda 2 are real, unequal and of opposite sign, then it will be a saddle point, which is obviously unstable. And if the eigenvalues are complex conjugate but not purely imaginary, then the critical point, the trajectory of the critical point will be a spiral, and it will be a stable spiral if real part of the eigenvalue becomes negative, and it will be a unstable stable spiral if real part of lambda I are positive. And in 4 case, if the eigenvalues are purely imaginary, then the trajectory of the critical point will be a center, which is a stable one. With this some sort of theory, now let us solve this problem. And in this problem, we are given that 0 0 is a critical point of the system x prime t is equal to x square plus y square minus 2x and y prime t is equal to 3x square minus x plus 3y. So here we are given that, let us denote f of xy is equal to x square plus y square minus 2x and g of xy is equal to 3x square minus x plus 3y. If we differentiate this partially with respect to x, then we have del f del x is equal to 2x minus 2 and del f del y is equal to 2y, del g del x is equal to 6x minus 1 and del g del y is equal to 3. Therefore, the Jacobian matrix evaluated at the critical point 0 0 is equal to del f del x, that is 2x minus 2, del f del y means 2y, del g del x means 6x minus 1, and del g del y is 3, evaluated at the critical point 0 0, which is equal to minus 2, 0, minus 1 and 3. Now let us evaluate the eigenvalues of this 2 cross 2 matrix. For eigenvalues, determinant of minus 2 minus lambda, 0, minus 1, 3 minus lambda, this is equal to 0. This implies minus 2 minus lambda into 3 minus lambda is equal to 0. This implies lambda 1 is equal to minus 2 and lambda 2 is equal to 3. Thus, one eigenvalue lambda 1 is negative and another eigenvalue lambda 2 is positive. And from this table we see that lambda 1 are real, unequal and of opposite sign. Therefore, the critical point will be a saddle point, and hence the option 3 will be a correct option for this problem. Thank you for watching.